Griffin Group. Let's have it. I'll choose. Griffin Group. Go. Griffin Group. Go first. Please, Griffin Group. I know that you're there.
Yes. Should we just say what we've been doing, or?
Yeah. Of course. If you have the song, it's even better, right? If you have the song, it's even better.
I am sorry, I have not had the time to make a whole song.
No, then zero. No extra points for you guys.
I didn't know it would affect my grade.
Yes, of course.
No, so we met up.
No song. Look, I've read it. No song equal no extra point. Go ahead.
We met up and we discussed how
physically. You met physically.
Yes.
Wow.
We communicate and split up what we wanted, what everyone should do.
Okay.
And the person in charge of task 1 has already started and has already created a Google Colab, and I have not been able to test everything, but it looks kind of almost done.
So how many active team members do you have?
We have all 5 of us are active.
Wow.
We couldn't meet all 5 of us, but the last person told us in advance and asked what they could do, and yeah, the communication was tough.
Very good. Okay, great. Yeah, any other comment, anything else that you want to share?
From the dude who did the code said that he would be willing to maybe talk a bit about the progress.
Okay.
But I don't know if he is in the call at the moment.
Hello, I just arrived.
Right in time. So I want to let you know that your team leader didn't do the song, so you guys lost the opportunity of getting extra points, okay? But you blame him.
I will say that. No, we didn't. That was my bad, guys. My bad.
Just joking. Go ahead. Tell us about the progress. Yeah.
Okay, so let me just share my screen. So basically, I was assigned the part of doing the classic KNN algorithm. So I will show you my collab file. We were working on it on a collab file. Okay. I think you guys can see it.
Yeah.
Well, okay, so here's the link where we get the data from the dataset. And then I look at the fields we had. So we had some more things that we saw on the paper. I think later I did an analysis, and because I found no correlation between these sigma values, I just discarded them afterwards. We'll see that later. But okay, we have lots of values, and something that I wanted to do is this file object, like this potentially hazardous asterisk, I think. I converted it later to just Boolean values because it was stored as strings, like yes or no for hazardous or not hazardous. So later on, I modified that.
Okay, so it's a binary. It's a binary variable.
Yeah. But
that's part of the challenge for everybody, right? So part of the challenge, because we haven't discussed it yet, so I want you to discover it, is that once you have a mix of continuous and discrete variable, you have to be very careful. You have to be very careful on how you handle them. Okay.
Okay. Oh, so that was one of the different values, and then these are the values that we had as objects instead of just numerical values like float64. And then I just printed some random sample of these columns to see if they are null or not. Okay. Yeah, and I then later on inspected that we have a column that it was just all the same values, like this equinox. So yeah, it's not very helpful to us.
Correct. So some feature selection is necessary.
Yeah. And then I expected the class, since we were gonna use this to make our predictions. And I saw how many like the distribution. I forgot to plot a graph, but we can see that we have more of this kind of object here, more of this kind of class. So I think this overrepresentation of this one may be something that I'll consider later when we make the analysis. Okay, and then this is what I was talking about. We just changed these dangerous label to Boolean values, like instead of these true and false.
Of course.
And then and I did this heat map to see if there were any correlations between the data. But actually, I didn't use this later on. So the next step was I tried to use a KNN algorithm, but built in a library before I built my own.
Of course.
So let's see. Okay, so I just took all of the numerical values and I put them like as features, and then my target feature here. Okay, and then something important to say about this part is, let's see here, scale.
Standard, yes, you're scaling the data.
Yeah, because the different magnitude we have in the between the values, so that could lead to some imprecisions in the model. And then maybe here, I had to fill many missing values. So I look at I think I don't have the code here because I'll delete it later, but I found that many attributes were missing. So my model will have lots of problems like that, and I didn't know which strategy would be better to just drop if I just drop the columns, I will be missing so much data that it will be working that way. So I just tried with this one with mean strategy. So whenever I found missing values, I just calculate the mean for that column and I fill it with like that.
Do you know how this is called in data science? How do we call this? Do you have a name for it? Because what you did is very reasonable, right? And it's something that people do all the time. It has a name, which is called data imputation.
Oh, yeah.
When you have a missing value, data imputation. You have a missing value and you don't want to throw away the dataset entry because you miss one value. So you come up with a value to substitute that. It's called data imputation. Go ahead.
Okay. So here's the part where I just train the model and then I do the predictions. I just try to run it like some minutes before, and it will took a little long, so I just stop it. But here I have the results from that prediction, and it turned out to do pretty well for most fields, for most classes. But here we have, I think if we look above, we will find that this is one like misrepresented class in the dataset. But I think the result is pretty good for most of the classes. So, but I have to say that this is not my model yet. So I was trying to find my.
Yeah, of course. I mean, you are encouraged to use the built-in libraries, right? So you don't have to build the algorithm yourself from scratch, right? So you can use the built-in library. But of course, the tricky part is to, like, the rest of the challenge, you have to come up with some implementation which is yours.
Yeah. Okay, so that's until here, and then I try to implement my own class, my own KNN algorithm.
Okay.
Here's the definition, and it's quite straightforward. Here I have the the function for this.
You just use an arc sort.
Yeah, but I couldn't make it to predict something yet. I was, it is running for too long already, so I think it must have some problem.
So you have to mini batch it, right? You have to mini batch it.
Yeah.
You know what I mean? Yeah, you will have to do some. So because here you run it over the whole data set once, right?
Yeah.
But
So
the excess is very large. So what you will do is that you will create mini batches, right? And then you just run it over a mini batch, and then you repeat, you rinse and repeat.
Yeah, so I should do that later.
Okay.
Yeah, that's the progress until now. So
you see that like this, we discussed this, right? So the implementation KNN is very heavy, right? Because you have to, when you want to do inference, you have to compare every entry in the test set to every entry in the train set. So it is computationally very expensive, right? So be careful and don't.
Okay, so I think that's
okay. Very good.
That's all I have for now.
Very good. Okay. Yeah. So I think I'm happy that you guys are all active. The progress is good. And yeah, so everything very nice, very nice.
Okay.
Good. Okay. Who comes next? Who comes next? For example, harmonic harpies. You want to go next? Harmonic harpies. Come. Okay.
I can speak up then.
Come again?
I can. Can you hear me?
Yeah, I can hear you.
Okay. Yeah, I'm not sure if someone already started in the code, but we created the song at least.
Wait a second. Before we do that, can you tell me how many members are active?
Active, we are 5 in the line group, and active, I would say 3. Yeah. So we created.
So, but the line group was formed. The line group was formed on Saturday, right? When we declare. Hi, I'm trying to say this. The group, you formed the line group when we released the members of the group, right? So everybody made an active effort to join the line group in the last 3 days, basically, correct? Oh. Hello?
Hello?
You hear what I said?
I just had a connection loss the last.
I said that
seconds.
the group. Yeah. Are you okay with it? Can you hear me now?
Yeah, perfect now.
I said that the group was created, let's say, 3 or 4 days ago, right? So in the last 3 or 4 days, all the 5 people made an effort to join the line group. That's what I'm saying. Is that correct?
Yeah, all people joined the group. Yeah.
Okay, good.
Okay,
go ahead.
I can just try to play it here from my phone into the chat. I hope it works.
Is there anybody from the harmonic harpies here? So maybe they can do it from their side. No. Okay. Go ahead, try. Give it a try.
I have it as voice mic here. Up here, you created the song, right?
I have the file, but how can I play it on the?
So do you have it in a player in Chrome?
I have it.
Because you can share the Chrome tab. Over the Chrome tab, you can share the music.
Can I just share my I have it as an MP3, so I can just share my media player, no? Or
okay. So, can you try to open it with the Chrome tab? You open them between the Chrome tab.
I don't. I can try.
Just drag and drop should work. There should be. Should be an MP3.
That works.
Then you share the tab and you enable the sharing of the music.
Okay. It's a pretty long song though, so maybe just
just listen to it. But do you have the lyrics? Do you have the lyrics of the song?
Oh, the
lyrics are very important.
I can, because I made it with Suno.
Okay, so you have the lyrics.
So I can play it in Suno, yeah.
Okay. And show us also the lyrics, okay? We want to see what is the.
Yeah. I'm coming. Just give me a second. Let me just. Yeah. Okay. Okay. Show screen.
Yeah. Enable the sharing of the music when you share the screen, right?
Yeah. For some reason, I can't find my Chrome tab.
It's okay. You just started using the computer 20 years for the past 20 years.
I wait. Sorry.
You can do it. I believe in you.
I'm trying my best.
You got this, Pierre. We believe in you.
We believe in you. Okay. I just, for some reason, it's pulling my other tabs. I can't. Yes. Boom. That's my Slack.
You can also share the You can also share the link. You can make the song public and you can share the link.
Okay, I found it.
Okay.
Allow. Okay. Can you see this?
Yes.
Can you hear it?
No. Did you enable the sharing of the music in the tab?
There was no
So we-
option to.
Yeah. So, go click that one. Click the share button. Click the share. So everybody listen. Click the share button. Present something else. Yeah. Then select Windows screen.
There's just mute website notifications.
Where are you? Are you on Ubuntu or something?
Oh yeah, I use like a Firefox thing. Does it have to be in Google Chrome?
Yes, correct.
Then
Doesn't
no,
matter. Just send the link to the song in the. Just send the link to the
Okay.
song and then we'll send the link of the song in the.
Share.
In
Copy
the
song link. Okay. Sorry about that.
yeah.
Share. Copy link to clipboard.
So you have to make it public and then you share it. Yeah.
Oh right. Okay.
Yeah.
Public. There you go.
Okay, let's listen to 2 minutes of song, then we'll go back to the class. Okay. So I'll show you how to do it. So you share this, then you also share the music. Once you do the share the Chrome tab, and now if you play it should be there.
In the realms of code so high, every line you write, gonna make the darkness bright. Typing dreams and keys, unlocking worlds with ease. Through the binary night, you shine so pure and bright. Fly high, a little heartbeat, in the digital sky so free. With the power of your mind, you leave the shadows behind.
Guys, too much Katy Perry, okay? And you can do better lyrics, okay? Go back and refine the lyrics, please. But it's good, but it's too poppy for me, okay?
My bad.
Okay, very good. Anything about the code that you want to discuss? Anything about the challenge? Guys, anything about the code that you want to discuss? Yeah.
We haven't really started anything
Okay.
yet. To be honest, I'm not sure where our leader is, but
What do you mean? You
nothing
don't
has
know
been,
who's your leader?
his name is. Oh, he said.
Huh?
Sorry, I'm very bad with names. His leaders, our leader's called Andrew. I don't know if he's here in the call. But we haven't started on anything. Nothing has been organized.
But why is the leader missing?
Oh, there he is.
Andrew. Why weren't you responsive, Andrew? Tell us. Andrew, come tell us. Is everything okay? Andrew. Andrew, come talk to us. Listen, Andrew, you're supposed to be the leader. You're supposed to lead, okay? If you cannot even take care of leading the group, I'm not sure what to tell you, okay? So try to be active by next time, right? I mean, you know that you have to present for the elevator pitch. So what can I do for you? Yeah, hopefully Andrew gonna do better by next time, guys. Okay, it's gonna be more responsive. Okay, very good. Yeah, you guys try to give me something by next time. Okay, Andrew, please. You have to lead. Okay. Okay, next group. Who do we want to do next group? Quetzalcoatl. God damn it. Quetzalcoatl.
Here?
Yes. You know to
set up.
pronounce it.
No, not actually.
Okay, very good, very good. Is there anybody that knows how to pronounce the name of the group? Or...
Sorry for that. That was my idea when I was in there.
Quetzalcoatl.
Quetzalcoatl.
Yeah.
Well, come again, come again.
Quetzalcoatl.
God damn it. I thought the Chinese were difficult to pronounce with the tone and everything, right? Okay. Please give us a WAV file that you can share in the group so that everybody knows how to pronounce it. Okay, go ahead, Joyce. You're the leader, right?
Yes. So we have a group of 4, and so far we've been working well with each other.
Okay.
All the group members are active in the group chat. We are using Slack to communicate.
Okay.
And
Because I made a group for you guys, right? I made a group for you guys. If you don't want to use it, it's fine. It's just that if you want to talk in that group and you have some question for me, I can answer in the group you know what I mean. If you ask me a question, you don't have to. You can ask me in the group. Wait a second. Quick copy link.
I see.
Yeah. So because then if you ask questions, then I know that the question comes from the group, so I can remember who was asking me what. Otherwise, if you use the general channel, just a mess. Okay, go ahead.
So I've created a song, and
Okay.
let me share it to you.
Is it gonna be Korean pop? Is it gonna? Where is it gonna be? That's it.
No, it's not Korean pop.
Let me see if I can guess.
So here it is.
Let's see what she's. Let's see. Okay, let's see. Oh, rock. Okay, let's see.
Okay.
Staring at screens all night, the dead are running in lines so tight. Asteroids, no bird in sight. Space whispers, secrets and bites. Code is our language raw. Nothing stars we never saw. Beginner roars without a flaw. Bites and bits in an endless straw. Code is our language raw. Nothing stars we never saw. Beginner roars without a flaw.
Right?
Bites and bits
Avril
in an
Lavigne.
endless
Yeah,
straw.
very Avril Lavigne.
This is very
The
old.
data miners of the night. Through the cosmos our code takes flight. Stars and asteroids in digital light. In the vast unknown we'll fight. Algorithms in our veins. Space
Let me know
routes
if
and
I should
binary
pop.
chains.
It's good. I think you can work a little bit on the lyrics, but yeah, it's very Avril Lavigne, right? Okay, good. What did you use to generate it? Which AI did you use?
This AI is called. Let me see.
Is that an OpenAI one? How is it called?
I don't know what it's called.
Okay. Yeah, there is no name for the. Yeah, there is no name for everything. I think they just steal from. How did you find this? It's possible that they just steal from Suno or from someone else, right? What? Where does this come from? You see what I mean? There is no name of the company, no name of the product. AI music.so. Yeah, it's very fishy. I think they steal tokens. I think they steal tokens from Suno, from somewhere. Yeah. And then you don't have to pay. Well, pricing. Okay, so you have to pay for it. Okay, good. It's not bad.
Yeah.
Okay, go ahead. Tell us something about the challenge.
So
Also, post the link of
for-
the song. Post the link of the song in Slack, please, so we can all listen to it.
Okay. So
Yeah, everybody post the link of the song. Make the song public and post on Slack, please. Let me do a tag. Group leaders. please post your song link as a reply. Okay, so post as a reply to my link. Okay, go ahead. Tell us about the challenge.
So for the challenge now, we've distributed the work to everyone, and right now we have, you can see our. Let me show you the collab file. So most of the team members are quite busy this week, so we've only done importing the data set into the collab file and also kind of just exploring its shape and all the properties of it. So the next step would be data cleaning and also the imputation that we just talked about. That is all for our group right now.
Very good, very good. Yeah, so because Joyce, you see, as a leader, you have to prevent this, right? Because as a leader, the students, they reason in this way. They always push the job to the last moment. And it's really, and then really when you do that, you waste more time because then coordinating at the last moment is very costly. So you have to try to push people to work more like more regularly, right? If you ask somebody, they will tell you that they're busy this week, right? So you have to try to get them to work more regularly, right? Because students really, they work like this, right? They work in peaks. So yeah, anyway. Okay, very good, very good. Anything else that you want to share? Anything else that you want to say?
That would be all.
Okay, very good, very good.
Thank you.
Ciao, ciao. Okay, next group. Who's the next group? So who's the next group?
I think we
Alicanto, you
can
want that?
present
Okay.
now. Yeah, Alicanto. Yeah.
Good.
Okay. Hello, everyone. Yeah, this group just made a song as well, but as I'm on Firefox right now, I can't play it. But I don't know if someone
you can
just
send me
want
the
to make
link.
me a
You
favor.
posted the link.
Yeah.
You posted the link. Okay,
Yeah,
let me
it
do
is
it.
in the Slack group.
Okay, let me do it. Let me do it now.
Okay, it's a quite long song as well,
we
but
just
maybe
listen
like
to
with
it and
the
then
first
yeah.
minute, I think it will be okay.
Let's see. Yeah, you guys have to work more on the lyrics. I think generally the lyrics are a little bit lackluster.
Almost the same.
You have to be more
I
poetic.
think the prompt maybe was almost the same for all the groups.
Let's see. Electronic rhythm pop. Let's listen, guys.
Late nights, glowing screens, we're a team with one dream. Rows of data flow patterns start to show.
Okay.
Scattered plots and lines, hidden in the signs, seeking out the trend till we reach the end.
Okay.
Crunching numbers, we can fly, finding truth beneath the sky. Data waves we ride so high, breaking codes will never die.
Oh, they look for it.
Rhythms blend, let the data bend. Through each graph we find secrets left behind. We'll never die.
Never die.
Algorithms blend.
Okay, good. Did work on the lyrics, right? Because breaking codes will never die. Why are you dying? There is no reason to die. You're doing coding. You're coding, right? Yeah, work on the lyrics. It's pretty good. Pretty good. And I don't know what it reminds me of. Some like French dance music or something.
Present,
Okay.
yeah. It was like dance music. I was thinking about that.
Very
Yeah,
good. Tell us about the challenge.
we just about the challenge. We haven't finished it yet, but we have already started.
How many
Now
people are active? How many people
we're
are active?
five. We're 5 members currently: Sain, Aaron, Cecilia, Jean, and me. Luckily, all of the members are very active and collaborative. Each one of us, has already like the duties assigned, so we are
Okay.
working on it.
Okay.
We try to adopt like a divide and conquer approach, let's say,
Okay.
to work on this challenge. So like, for example, Ty and Aaron are working on the coding part, the
Okay.
hard part, and then Cecilia and Ty are working on the notebooks presentations. Then Jean will be in charge of the PPT presentation for the
Okay.
final elevator pitch.
Okay.
I'm trying to keep all together, all of this together, and try
Yeah.
to reinforce any part of the
Okay. Very
like
good.
any group if they need like some reinforcement.
Do you have anything that you want to discuss already? No. Yeah,
As I said before, we have not finished the challenge,
okay.
but we have already started on the work. I mean,
Okay.
to work on the code. But I'm not the most appropriate to talk about that. I don't know if is here on the call some
Yeah. If
of
you
the
guys, somebody
code
wants to talk, if somebody wants to
of the
discuss the code,
coders
then,
to want to share to talk about the code, maybe Tying or Aaron. I don't know if they're here right now. Oh yeah, we have already.
Can you hear?
Yeah, I can hear
Okay,
you.
I'll share my screen. Can see the screen already.
Yeah.
Okay. Yeah. Zoom in a little bit for us, please. That we are on. Very good.
Okay, so basically we just loaded the data set, looked through it. This is just cleaning, so we just dropped all the rows with missing values. Then replace all the columns that had like strings to like ones or zeros.
Correct.
For those that are yes or no, they're replaced to 1 or 0 for the KNN classification. Then for the class, they're all changed to numbers for encoding so that can use for KNN later. Yeah. Then after that, we just split the data set into train and testing. Tried doing the classic KNN algorithm development already. I used a KD tree for the data structure so that it would run a little bit
Wait a
faster.
second. So you use a KD tree for the data structure with what purpose? Tell me.
So the KD tree is essentially just it organizes all the points in k-dimensional space. So it's like very efficient for doing the nearest neighbor searches that the KNN algorithm uses.
I agree and disagree, meaning that when an inference point comes in, right, you have to take the difference between the current features and the features in the and all the features in the data set, right? So tell me, and then this difference, right? In general, it's unordered, right? Like if you have the elements, right, and you order the elements, let's say according to some ordering, right? Then you take the difference between your test sample and the elements in the data set. What you obtain is an unordered list of differences. Do we agree?
Yes, I think I get what you're saying. Yeah.
Let me just give you an example. Let's say that you have a data set, you just have one feature. Let's say that you have 10, I'll write here. Let's say you have 20. Let's say that you have something like this: 20, 17, 15, 8, 3, 8, 4, 3, 2, and 1. Okay. Then another point comes in, which is equal to 10, right? Then you will get 10. Then the list of differences will be list of differences. Oh gosh, list of differences. List of differences is equal to 10, 7, 5, minus 2, minus 6, minus 6, minus 8, and minus 9. Okay? And then you have to find the neighbors over this distance. So you look at the mean over this distance. Correct?
Mm-hmm.
So this works well if you do it dimension by dimension. Okay? If you do dimension, sorry. This works well if you have one dimension, right? If you have one dimension, you can do a KD3. And for each features, you know that in order to find the difference, you are all good, right? But now if you have a data set which is equal to, there has two features, let's say that you have 20 and 1. You have 17 and 20. You 17 and 10. You have 15 and 4, right? Then when you take this difference, you can no longer do this trick, right? You can no longer do this trick. So I agree with you that you could use a KD3 to find the differences, but the KD3 will work only on one dimension at a time. So if I were you, I will do this, right? I will be like, okay, among the features that I need, I know that the one feature is gonna be the one that is, let's say, the most expensive or the most informative. So I can do a KD3 over that feature and organize over that feature, so that then during inference I can speed up finding that the difference on that one feature. But in general, the KD3 will not. You know what I mean? You cannot organize the KD3 so that you minimize the high. You cannot come up with a KD3 that does the job of finding or speeding up the minimum of the differences across multiple dimensions. So yeah, so I agree with you that if you can boil down your differences to just one scalar, then the KD3 will allow you. Otherwise, it would not necessarily work. Was I clear enough?
Yeah, I got it.
Okay, good. Okay, go ahead.
Yeah, so then just build a function for evaluating the classifier, then went through different values for K to see how it worked.
Okay, tell me about the confusion matrix.
The confusion matrix is basically it tells you like the true positive, true negatives, false positives, false negatives for each of the classes.
But you see that, for example, the third row and the third column, you have 0 samples in the class, correct?
Mm-hmm.
Yeah, so you have a lot of you have some classes that have 0 entries. Is that because you just use a small batch? No.
No, for this one I use the whole data set because the data set has very little in some of the classes.
Correct. So there is something missing because there should be all classes should have at least one member, right? You see that?
Yeah.
So there is you are missing something there. Yeah. Class 3 has 87 entries, and you see that you in class. Did you order the classes as in? Yeah. So is this the confusion matrix for the same classes?
Yes, should be, but.
So you see that you see that class 3 you don't put anything in class 3, and you have no elements in class 3, so there is something missing there. Do you agree?
Yeah, because later on I did I stratified while doing the test and training split, so that to ensure that the proportion of each classes stay the same. But I think for this one I didn't.
Just making sure that just making sure that it makes sense. Okay, go ahead.
Then afterwards, that I tried looking at the weighted one.
Okay.
So like because I realized it was taking very long to train, so it's a little bit out of order because I did like some extra more like cleaning to take out more to use lesser features so that it will go faster.
Do you do any data imputation for the missing data? What do you do for the missing data?
I just dropped all the rows with all the missing data.
That there is a choice. There is one choice.
Yeah. Then I just I just tried like using lesser features.
Of course. Feature
yeah.
selection, very good.
Yeah. And this is me just trying out with the inbuilt classifier to see whether like dropping the features did anything. Yeah.
Of course.
Yeah.
The feature engineering is very important, right? Yeah.
Yeah. That's about what I tried with the third one. Yeah. Then I just tried I resplit the training data by extractifying it this time. So I think my thing doesn't. I think the matrix didn't save for this one, but yeah.
Yeah, probably you stopped it because it was taking too long.
Yeah, because it was taking too long.
Of course. That's all for you to understand, right? Of course, as you said, k-nearest neighbor is very heavy, so it's tricky. But I like the idea of the KD3. I like the idea of the KD3 in this sense, okay? Let's see if I can find an image. KNN, KD3. So where did you come the idea of the KNN for the KD3? Where did it come from? Did it come from you? Did you have where did you study KD3?
Because I was looking at how Scikit did their KNN classification. Because I tried running that first, then I was doing like the regular the more like brute force. And then I was wondering like why the one in Scikit ran a lot faster. So I went to look like what they were doing to like what solve data structures they were using to make it faster.
Correct. So because what you realize is this, right? So the KD3, I mean, depending on how it's implemented, right? But usually the implementation is doing this type of boxes, right? So for each feature, so just for everybody to understand, right? So the KD3 is something like this. You have a tree, and on each you have a tree. On each node, you take one feature and you split the data on one axis of the over one threshold for the feature. So let's say that this is feature 1, is the root of the node. Let's see if I can go here. Here. Okay, good. So this is, let me zoom in. Can I zoom in? So KD3s are usually computer sorry, let me share something. Okay, something like this. Okay, it's KD3s, they work like this, right? So what you do is that you take, let's say, feature 1, and you choose a threshold for feature 1. You say feature 1 is greater than the threshold and smaller than the threshold. Then I will give a label to my element. I will push my element to either left or right. And you repeat this over multiple features, and you can also repeat the features. So at the end of the tree, you give a label to the point, and you say, oh, this label belongs to this region. Okay. So this operation, what does it correspond to in the feature space? Let's say that we have 2 features, so we just have x1 and x2. So you see, for example, that if we split over x1 at the first level, we are splitting the points in these 2 regions, left of this, right of this. Then when we go inside this tree, we are splitting over this region versus this region versus this region, and so on and so forth. So of course, when you repeat this in higher dimension, then you are using these boxes, right? You're creating these boxes for clustering the data. And then what you can do, right, is that you can say to all of this data, all of these boxes, I construct them so that I have a unique label for the points I. And let's do a step back. So you understand how this data structure works. Then imagine that these points are colored, and each color corresponds to a class. So let's say that we have black points and red points. What you can do is that you can construct the KD3 so that when the points that are classified in these regions, they all have the same color. So they are all associated to the same class. Okay? And then, of course, if you can build a tree that classifies the points using this, then what you can do is that you can completely disregard the data set that you have. And once an inference point comes in, you just go along the KD tree and you classify the points according to the color of the leaf node. Okay. Is this clear? Was I clear enough? Yeah, sorry guys, we are improvising, right? So yeah, give me a thumb up if it was clear. Okay, so of course this data structure is very, very quick, right? But basically finding the thresholds of the KD tree so that you create a tree of minimum height, such that in each point you have only one class. It's as you can imagine, it's a much harder problem than the one that we are facing now, right? So I agree that KD trees are a way to speed up the solution, okay? A way to speed up the solution, but yeah, of course, you haven't seen the algorithm in order that allows you to train a KD tree that does this. Okay, everything okay, guys? Give me a thumb up. Okay, very good. So yeah. So any other comments from the Alicanto group? Anything else?
I think this is all from us.
Okay, very good, very good. Okay, good job. If you can, if you can, if you want to discuss more about this KD tree later on, it would be great. Because this is also connected to clustering, right? So we're going to see this type of algorithms later on when we do clustering using random forest and trees. So it's nice. So if you want to tell us something more about this next time, it would be nice. Okay, very good, very good. Next group. Who wants to go next?
I think we are the last one. Wan Zhetong.
Okay.
I don't know if Julius is in the call. I will look him to present, but if he's not, okay, we'll go ahead.
Okay.
I think he's not in the. Okay, so far what we got is first we imported the dataset from the page of the author that posted this dataset. The first thing that we do is print the first rows of this dataset to see what it contains. Check if there is missing values in the dataset. So
Okay.
far, we got, for example, in name there are like.
Can you zoom in a little bit?
Yeah. I can see it.
Okay, go ahead.
Also, we classify the data in the dataset if it's numerical value or if it's a categorical value. For example, for the class, we had find how many entries are for each class here.
Good.
To reduce the dataset and delete all non-necessary features, we have delete the columns that we are not going to use in the creation of the KNN model. And also we had convert to binary the potential hazardous of the asteroids to 1 or 0 if is potential hazard or 0 if it's not. Also we have split the data to train this to train the model, and we have not started to code our own KNN model. We have just imported some libraries and try to see what does it gets us as an output. But I run into problems here because for the predictions, the code runs too slow. So I start looking for another options. one of the options was to reduce the sample to 5,000 rows. Here I just reduced to 10, but the code is still getting errors, like it's taking too much to run, like 10 minutes, and it doesn't give any results. So I look for another options, and even asked ChatGPT what options can be, and one of the options was the one that you has just show us, that we can change the algorithm to Val3 or to KD3, but I have not explored it further yet.
Stay there.
Yeah.
Go back to ChatGPT. Go back.
Okay.
You see this suggestion to use PCA? Go down a little bit. Go down to this suggestion to use PCA. The next one.
The next one,
yeah. Do you understand this one here?
Yeah. If just in case we have too many variables, let's say that we have like 100 columns, to reduce the dimension of the dataset in the principal component in order to analysis. But
does it make sense to you? Does it make sense to you to do PCA?
Yeah. Just for example, let's see. For example, if here we are just going to use like 5 or 4 variables, we don't need the 35 columns or the 100 columns in order to perform these calculations. So we are just taking what we just need. But in this case, the size of the dimension is not too big. It's 35. It's not 100. It's not 200. Another option was to sample the subset, like taking, for example, like 5,000 rows or 100 or 1,000 rows of the column for testing. Yeah, I have tried, but still getting some errors, so I have not solved it. So we just
just tell me, how many team members and how many are active?
We are 14 members and only 2 of us are active.
I see.
Like so far, Julius has helped me a lot. He code like 80% of this. I just try to understand his code and complement it and try to correct some errors. If you can see in the chat, we create a group and added the other people, and it's just me and Julius chatting, sharing the. This is so far that what we got.
Yeah. So as I said, apologies, but there is. So some students, they just drop the course and they don't tell us, so we put them in groups and then they don't reply. So it's not much that we can do about it, right? So, but if you're okay with 2 people working on it, then it's fine. Of course, we understand that you can do less since you're 2 people, but hopefully, let's see. Hopefully, the situation will improve.
I shared the song of my group in the.
Do you want to play for us? You want to play for us, or I play for you?
Can you play for me, please?
Yeah, of course. I don't do enough for you, right? I also have to play your songs. Guys, it's so difficult to be a professor. So difficult.
It's okay. I think
nobody appreciates you.
Julius helped me a lot, so I don't have any complaints about him.
Do you know why he's not here? Do you know why he's not here today?
No, I don't know. I thought he was going to join to the meeting.
Okay, no problem. Let's hear it.
Skies are white tonight, shimmering bright, alright. Counting stars one by one till the night is done. Planets dancing light, cosmic tale so divine. Through the dark we see the light shine through endless night. Counting stars, 1, 2, 3. Worlds beyond what we can see. Universe in front of me, breathing in the galaxy.
Guys, there is no reference to your group or to your group name or to the spirit of the group, okay? So fix the lyrics by next time, okay?
Okay.
Okay, so
Gonna fix.
by next time, guys, I want to see the group spirit emerging from the song. Okay.
Okay.
I want to see for everybody. Yeah, this is true for everybody. I want to see that there is a meaning behind the lyrics. Okay. Okay. I suggest we take a 5 minutes break. Then, as I said, in this week and next week, I'm teaching a quantum machine learning class at here at Polytechnic of Milan. If you want to come to the class, I pinned the link, so you can come to just listen in case you are interested in the topic. And so today, Elton will do some live coding after my class. So I'm going to go for like half an hour, like last time, a pretty short class. And then, Elton will do some live coding. As I said, let's try to minimize frontal teaching in that sense, right? So there is no, if you want to follow me, discuss something, you come, you follow me. But of course, there are so many resources for these topics that you don't have to come follow me. So just come if you think there is something useful for you, okay? We don't stress guys participating to frontal class in any way. Okay, so I'll see you back at 30, okay? I'll see you back at 8:30. Go walk around, drink some water, stay hydrated. Enjoy the songs of your teammates, and then we resume at 8:30. Okay, ciao, guys. Exciting at me. As always, we thank our people at Harvard for the slides. So as we said that we are discussing a little bit now. We discussed linear regression last time, and now we can discuss model validation a little bit. So at the beginning of training machine learning models, what we do is that we always separate the data into train and test. And we know that this is important because on the trained data, we obtain the parameters of the algorithm. And on the test data, we obtain the measure of performance. And we know how important this is to fully separate the trained data and the test data so that we have two independent numbers that, let's say, that they give us an independent view of the performance of the algorithm, right? So sometimes people are like, oh, well, why don't I use my full data set for training, and then I just pick some random points in the test in the data set for testing, right? Why do I need to separate train and test? Because effectively, I'm throwing away 20% of my data that I'm not using for training. But actually, this doesn't work, right? This is, as I always say to you guys, right? Sometimes finding the correct hyperparameters for the problem is just as important as having an algorithm to solve it, right? So you can imagine that if you have to test, for example, the choice of k in the k nearest neighbor, you have to have a completely new view of the data, okay? Then sometimes you further split the trained data into train and validation. And this is because sometimes you want to train the parameters of the parameters of the algorithm on the trained data, then use the validation to, let's say, choose some aspect of some hyperparameters of the algorithm, or to, for example, you are training a deep neural network. You use the trained data to obtain the gradient and to obtain some model updates, and then you use the validation data to update the learning rate. Okay, so there are some hyperparameters in the algorithm that you want to be able to modify during the training process, and for this reason, you set aside the validation data. So now your useful data that you use for training is even more used, but as we always say, finding the hyperparameters is crucial. And sometimes what you want to do is to have cross-validation. So what you do is that you chunk off the trained data into multiple subsets, and you train an algorithm over this different set of trained data. And basically what you obtain from this is that for each of the trained data that you have, you're going to obtain some distribution of the model. And by looking at the distribution of the parameters that are obtained from the trained data, you're going to obtain a distribution. The distribution is going to give you a confidence on the data. Okay, so what we discussed before is how to select the model to avoid overfitting, validation and cross-validation of the model. So now we can discuss about the generalization error and trade-off. Guys, the group call has been limited to 15 minutes. Do not ask me why. The setting of the calls are very, very strange, guys. So once very, very strange things are happening here. Anyway, so in 15 minutes we switch link, okay? So no worries. So now let's discuss generalization error, bias, variance trade-off, regularization, last and reach, okay? So as we said, let's say that we have a certain model. What we have are the different number of parameters for this model. So let's say that we are using a polynomial to interpolate the two-dimensional data set, okay? So on one side we have the x, on the other side we have the y, and we just want to find the relation between the x and the y, which is described by a polynomial. What we can do is that we have a hyperparameter, which is the degree of the polynomial that we are using for fitting the data. So what happens is that we have an ideal number of parameters. In this case, you see that we have let's say a 2-degree polynomial, or maybe a degree 4 polynomial, that give us the best fitting of the data. Then what we can do is that we have fewer parameters than what we need. So for example, if we only have 2 parameters, then we're going to have a linear function, and this linear function does not fit the data. So we can still find the best linear interpolation of the data, but of course, we are not performing particularly well. And so what we can do is that we can also choose, for example, a degree 16 polynomial, and we can have we can have this behavior, right? We can have this fitting curve. And of course, the error will be lower in the overfitting case than in the correct choice of the parameters. And we might be led to believe that the more parameters we have in our model, the better we are off, because we are fitting the data more and more, and we are basically reducing our error. But we see that the mistake that we made is that we are fitting the model to the elements in the trained data set, and if we have to reshuffle the trained data set, we will obtain a completely different model. So that clearly what we're doing here is that we are overfitting. Okay, we are fitting the model to the data instead of to the two trained. Guys, there is somebody with a drill going around. Let me close my window. They're building a new chemistry building next to me, so it's very, very noisy sometimes. Okay, so so now we recognize that there are two sources of error. So there is a reducible error, which is called also aleatoric error. Alias in Latin means dice. So this error, which is irreducible, is the error that is related to the measurement process. We said that when we obtain data comes from some sort of physical situation, some physical process, some environmental conditions that then is subject to error, right? So there could be errors in the sensor, there could be error in the recordings, there could be incomplete data, so that there could be some mistakes in entering the data, so that this error is intrinsic in the data. And whatever model you have that tries to relate your features to your output, you will never be able to remove this error, because this error is aleatoric, is completely related to the measurement procedure. And then there is a reducible error, which is called epistemic error. Epistemic is a Greek word that means knowledge. So it's an error in the knowledge. And this error comes from a bad choice of model, okay? So if you were able to choose a better model, then you will be able to reduce this error. So this error is reducible by a better choice of model, a better choice of parameter. But this is arising from overfitting and underfitting, okay? So it means that sometimes we use too little parameters to represent the data, and sometimes we use too many parameters. And so these are the two sources of error that we have. So you see that that then we are in this sort of loop, right? where what we are trying to do is always to find a sweet spot between in the choice of our number of parameters, so that if you increase complexity, you go from underfitting to overfitting. If you reduce complexity, you go from overfitting to underfitting, so that you're always trying to find a sweet spot in the choice of hyperparameters. And what you see is always this figure here on the right that says that the error is always decreasing with the model complexity, and we will call this the bias. Okay, so bias is the decrease of the error with the model parameters. Okay, now we can do we can discuss the bias versus bias trade-off. So here you see that you have different models, right? And for different models, what you do is that you subsample some of the data, and from the subsample data, you create a model. And this is the curve in red. And then you have a true model, which is the curve in blue. So in all these plots, we always plot the true model in blue, and this model remains the same. And what we do is that from the data set, we shuffle the data, we take a subsample of the data to train a model. So this is the case in which we have multiple batches from which we are building a model. And then what we do is that we build a specific model. So this is the F1 hat, which is the red line. So you see that the red line is slightly different for all these different plots. And what we are doing is that we are finding a linear fitting for this true model, which is locally linear, right? So if you look at this model locally, it looks almost linear. So if you keep repeating this procedure, you will obtain many different models. And what you can do is that you can obtain a variance of the parameters of the linear fit, and which is represented here, right? So the last figure on the bottom right is a representation of all the models that you obtain if you do this procedure of taking your data set, subsampling some of the elements, and obtaining a model. Very good. So you see here that for this linear model, we are very good, meaning that the prediction is all very tight, right? So we have some variation in the parameters of the model, but this variation is sort of reasonable. Say it's in the order of 5 to 7%. Now let's say that we take a fitting which is a higher order polynomial. In this case, we take a polynomial of degree 10. Then we repeat the same operation. We have the true model, which is the blue model. To the measurements of the blue model, we add some noise. And then what we do is that we subsample some of the elements from the train data, from the train set, and then we fit the degree 10 polynomial over these elements, and we then repeat this operation multiple times. So you see that these degree 10 polynomials, they changes greatly in these three figures, right? In the figure 1, 2, and 3. Why does it change greatly? Because the polynomial has a lot of parameters. So the polynomial is able to change greatly to adapt to the data. So here we have, let's say, 15 points, maybe 15 yellow points, and then we have a degree 10 polynomial. So what we can do is that we can really get the degree 10 polynomial to wave through the different points of that have been sampled from the train set. And we then we can construct models that they fit the points very well. Of course, this is undesirable in this situation because we have too many degrees of freedom, because we can describe a very large class of function with a polynomial of degree 10, but our true model locally, it's almost linear. So if we plot all the parameters, or all these possible fitting functions that we obtain after, let's say, we repeat this operation 200 times, what we obtain is a complete mess, right? There is no agreement in the model. And my degree 10 polynomials, basically, if I plot them all together, they cover the whole space completely. They have peak and valleys in completely different positions. So we are in this case, right, in which we see on the left that the linear model is fitting the true underlying model, and in the right case, we are just making a complete mess. So so this is the bias versus bias trade-off, right? So you observe that by looking at the variance of the parameters of your model, you can observe that you have a high variance when your bias is very low. So in the right-hand side, the error in each of these models, it's much lower than the error that you make in this model. Okay, this model, of course, it's a linear model, so you have very large differences between your data and your predicted data, your labels and your predicted data, because of course there is a lot of error in the measurements. So the bias goes down when we have more parameters, but of course the variance goes up. So this is the bias versus variance trade-off. So if you want a small bias, you're going to have a large model. But the large model corresponds to high variance in the parameters of the model because you are fitting the points excessively. So you might think that having a low bias is all you need, but of course this is not actually what you need, because if you have a low bias, this will signify that your model is overfitting. On the other hand, you would rather have fewer parameters and have a higher bias but smaller variance. Okay, and of course this is an art, right? This is where you need to think critically and observe and study and try to understand your model, because nobody will tell you, oh, this is overfitting, this is underfitting. Of course, it's an act of experience and real understanding of the data. Okay, so remember, so if you increase the complexity, then the bias goes down, but the variance goes up. So this is why it's a trade-off. It is a beautiful word if you could have a very small bias and very small variance, but of course, this is really the case. Okay, good. So this is if you have to remember anything from the class of today, it will be this image where we have this bias versus variance trade-off. Okay, simpler models, they have high bias, but they have very small variance. More complicated models, they have lower bias but higher variance. And where you want to live is in this nice point here. You want to find the point in which a trade-off between variance and bias is optimal. And of course, this is not an easy task. Otherwise, we will not be discussing. Okay, good. So here is some other models, right? So let's go through this. So this is a model in which we have a high bias and a small variance. So you see here that we are in the lower left quadrant. Then if we move to this other model, where the one with the polynomial of degree 10, we have high variance and low bias. So this we are at the two extreme of the bias variance trade-off. And what you want to do is something like this, to have low bias and low variance. So figuratively, the variance, you can represent this in a sense as the grouping of the models, right? So to have a low variance means that if you predict multiple models, they all appear in the same grouping. So this is what is referred to now. And the bias is small if this grouping is centered around 0. Okay, so you see here that this model is the best because we have a small grouping, like a very tight set of parameters, and they are concentrated around 0. And this is, of course, the best. And what is the worst? The worst is to have parameters of the model that are very spread apart, and they're also far away from the center. So clearly, this is undesirable for us. Okay, so let's discuss overfitting and underfitting. Of course, this term is used very generally. It's a concept which is applied to many situations, and different people have a different understanding of what is the essence of this concept. But the idea is that overfitting occurs when the model corresponds too closely to a training set, and as a result, the model fails to fit additional data. Okay? So far, we have seen overfitting can happen when you have too many parameters, when the degree of the polynomial is too large, and when you have too many interaction terms, right? So this is what we've seen so far, and this concept is kind of general and vague. But next, we're going to see linear predictor. So we're going to see ridge and lasso regression, and we're going to see how these models can be implicitly trained to prevent overfitting. Okay. Okay, very good. I think the call is about to end. Guys, I'll send another link soon, okay? I'll see you at the new link. I'll send it over Slack. I'll see you there. Ciao, ciao, guys. Question. Admit all. I'll let you with the jokes, okay? This is This is very funny, right? So this is just saying that the new programmers, they fall into errors very easily, but the experienced programmers, they do a flip in the air and then they do a stupid mistake. Yeah? This is the reality of everybody. See that we have a Pierluigi back here. So as you said last time, so we did the case of simple regression, right? When you just have one variable and one variable in input and one variable to predict. Of course, what you want to do is to repeat this for multiple variables. So let's say that somebody gives you a data set where you have a person and you want to guess the height, and you want to base the height based on, for example, sex and income, sex, income, and favorite number. And of course, you will always want to use as much data as possible for your prediction. But of course, there are some things that are relevant and some things that are not relevant. So, for example, sex is, of course, very important. I mean, gender, I should say gender. Gender is very important because we know that males generally have a higher height than females. Income, income is surprisingly related to height, but in a way which is not direct at all. We can have this discussion at some other point, why taller people tend to have higher income or vice versa. And then favorite number. Of course, favorite number seems to be a feature which is not related at all with height, for what is our understanding with. So we will want this relevance to emerge naturally from the process of predicting a person's height from these features. So before we saw this problem in which we were just predicting the simple two parameters for a linear regression. So in this case, we have an f of x1 as a function of x1. And then if we move to higher dimension, what we're doing is that we are finding a plane, a two-dimensional plane, that that passes through the points, right? That minimizes the distance between the point and the plane. Of course, the idea of distance between a point and a plane is a very well understood concept, right? You guys should be familiar with it. I think you must have done it in high school. And so this is the visualization of the two-dimensional vector. And then in general, you will want to say that if you have y labels from y1 to yn to predict from j features from x1 to xj, using a data set that has an xj that has this n values for the features from 1 to j. So you have n entries, and each entry is a vector from 1 to j. In this case, you will want to build a predictor, which is a predictor of this form, right? You predict all the outputs as a function of all the inputs, and so we can write this as a f hat, right? So you can say that we want to find the parameters of this hyperplane. So you refer to this as a hyperplane, a generalization of the concept of plane to higher dimension with a b hat, right? So the coefficient of b hat is a function of your dataset points. So let's go back to this idea of the budget, right? So what we have now is a design matrix, right? So we want to have we have an observation, and the observation is the TV budget for all of the different values. Now, if you want to complete the sales not only from the TV budget but also the radio and the newspaper, then we are building this matrix system. And for this matrix system, then we will obtain a prediction of the sales, which is a B0, which is the average value, plus a B1, the TV budget, plus a B2, the radio budget, plus a B3, the newspaper budget. Then you repeat this, you feed this into a nice matrix, because matrices allow us to see, to represent high-dimensional data very efficiently. So now we are baked as in the problem in which we have y equal to x times b. So notice that y is a vector, x is a matrix, and b is again a vector. Okay? So we can convert this high-dimensional problem to the solution of this vector equation, which is vector y is equal to the matrix x times the parameter b. The y is known, the x is known, the beta is missing. Okay. So this is how you represent in matrix form. Remember that usually the row index is the dataset index, and then the column index is the feature index. So you will write it as like this, right? The set of output feature y is the matrix x multiplied by the parameter beta, and now we want to find the parameter beta. Okay. So what we need is, with the concept of transpose of a matrix. So when you take a transpose of the matrix, we flip it over the side. In Python, you write this as np.transpose or ndarray.t. And then we have the inverse of the matrix. The inverse of a matrix is a matrix such that A times the inverse is equal to the identity matrix. In NP, this is in Python, this is np.linearalgebra.inverse. And now we have the two ingredients that we need in order to find the exact solution of this equation here, y is equal to x times beta. So if we want to minimize the MSE error between y and the prediction over the choice of beta, so x times beta will be equal to the y hat. This will correspond to this form, for example, in the two-dimensional case, in the case in which we have two input features. And the operation that you do will be to explode the summation. Then you take the derivative with respect to the two parameters, so in this case, the beta 1 and the beta 2. Then you will set the two of them to be equal to 0. And of course, you will not do it equation by equation, but you will collect everything to a matrix. So you have the derivative of the loss with respect to B1 and B2, now it's a vector, multiplied by a matrix. Then you will recognize that when you write this vector, this corresponds to exact x11, x21, x12, x22 multiplied by the y's. Of course, your choice is a choice of the beta, right? So you want to find the 0 of this equation in the beta 1 and the beta 2. So you continue with your derivation. Continue with your derivation. Then you write this part as a vector of y minus a vector of x multiplied by the beta. Very good. You see where we're going. And then you will figure out that in order to set this to 0, you have to set y minus x times beta equal to 0. And if you do that, then you will obtain the 0 of the derivative. Notice that the x are given to you and the y are given to you, and you're looking for the beta. So you have to set this equation to 0 as a function of the beta. So in order for this to be equal to 0, the x transpose y minus x times beta is to be equal to 0 in high dimension, right? So when you have a vector time matrix, the commutative property still holds. So you write this as x transpose y minus x transpose x times beta equal to 0. Now notice that whatever the dimension of x are, whether it's a tall matrix or a skinny matrix, then x times x transpose is a square matrix, and the beta n is the dimension of beta, and x transpose by y also has the same, is a vector of dimension of beta. So what we can do is that we can invert this matrix, left multiply both sides, and we have the beta as this expression. Okay, so the problem of determining the beta for a high dimensional data is as a closed form solution, and the closed form solution is given by this expression: x transpose x minus 1, then x transpose y. Okay, very good. So this, it turns out that the beta hat is the minimum of the MSE loss as a function of beta and as a closed form solution. This is very rare, and since this is very rare, you will never see another closed form solution after we move on from linear regression. And this is a treasure for us, right? We can understand a lot of things from this expression of the ultimate solution. But we will do so next time, okay? So it is 9 o'clock. Unfortunately, we stop here. And Elton is going to take over the class now. And and I'll see you guys next week. And next week we have the end of the presentation, the project 1, and hopefully everybody will be able to finish things there. Okay, guys, I'll go teach my other class, and we talk soon. Okay, anything else we talk over Slack. Sorry that for these 2 weeks we have this problem, and we have this thing, and then we return to our usual schedule. Okay, Elton, go ahead and take over. I'll leave you here. Ciao, ciao, guys.
So I'll just share the screen. Wait a minute, something is very wrong.